So now we talk about the closed loop, right? And the closed loop here, let me just write that down. We use, and here we're just going to talk about the cases that has a negative feedback. So let me explain what that is. So if you take a look at this op-amp, your output is being fed back into your input, right? So this is the feedback I was talking about. So if you don't have this, then this configuration is an open loop case. You just have your input going in somehow and then your output, and this guy has nothing to do with your input. That's the open loop. The closed loop is your output is being fed back into your input. And the negative feedback I was talking about was your output is being fed into your negative input. So that's why we call it negative feedback. It's not going to your positive. And in order to understand how this amplifier works, oh, by the way, this amplifier configuration is an inverting amplifier. And we're going to talk about a non-inverting amplifier and a voltage follower and a comparator circuit. I think, yeah, this one, but this guy does not have that feedback, okay? So those are the circuits we're going to focus on in this lab, and we now just talk about this guy. For all these op-amp circuits, if it has a feedback, if you use these 3 steps, you will be able to understand how the output is being connected to the input. This is the relationship you want to find out eventually, right? Because this is being used to amplify, say it's going to be 5 times amplifying or 2.5 times amplifying, something like that, which is your input is related to your output, right? So this is the 3-step derivation I have mentioned in the previous here. And let's check how this works. So the first step is we would like to understand the ideal op-amp assumption with the feedback, okay? In the previous page was, I talked about that already. This is just an ideal assumption in general. So this assumption works with or without that feedback. Even though you don't have a feedback, still this works. But the condition we're going to talk about here only works when we have a feedback, all right? And that thing is, first, let's see what V positive is. V positive just happened to be connected to 0 in this configuration, right? To the ground. So V positive value is just 0, okay? And your V out should be AOL times V positive minus V negative. And this guy just goes away because it's 0, and it's negative AOL. And if I just rewrite this, V negative equals AOL minus V out, what I just did was I just moved this thing to the left-hand side. So I have this. And since AOL is what? It goes to infinite, right? That was what we assumed. So the negative is 0 as well, because you divide something by infinite. So that becomes 0. So from here, we can tell V positive is V negative, and that just happened to be 0. So this is the characteristics when you have a feedback. And for this configuration only, it just happened to be 0 because they are the same, and this guy was just hooked up to 0, right? So they all became 0. by the way, in the next page, this guy is not connected to ground anymore. It's Vs, so it's not going to be 0. But still, these two are going to be the same. So don't get fooled that these are always 0. No, these two are just the same, and it happened to be 0. Okay. And next step is we would like to use the Kirchhoff's current law at the negative node, which is this guy here. So by the way, can anybody tell me what KCL is, Kirchhoff's current law? Yeah, exactly. That is, well, I call it flow in, is same as flow out. So first we need to define the currents. So for this node, we have 3 branches like that, right? So I would just call this IS because it's coming from the source. And this, I'll call it IN because that's the input current. And I'll call this guy as, okay. So if we, what are the flow ins? These two are flowing in. And this is the only guy that flows out. So we can have IS plus IF equals IN, right? And what's this IN? That's just 0 because we assumed that, right? In the previous page, we just talked about there's no current that flows in because the impedance here is infinite. In other words, it's like the circuit is broken, right? It's disconnected, I mean. So it's like this. So the next step is we find the I's. So IS is nothing but Vs minus V negative divided by Rs. Because you have 2 voltages and a resistor, then it's just the Ohm's law, right? Super simple, isn't it? And for this guy too, this is V out, V negative, and we have a resistor. So IF is V out minus V negative. So then what do we need? What do we want to do? We would like to sub these guys back in here. So if we do that, let me write that down here. So Vs minus V negative over Rs, that's Is, plus V out minus V negative over Rf, it's going to be 0. And what about this guy? How should we deal with this? It's 0, isn't it? You can just cross that out. And if we do a little bit of math, V out is negative Rf over Rs times Vs. So finally, we got this relationship. V out is negative Rf over Rs times Vs. So Vs and V out is being related by this ratio and has a negative sign. Okay, so if I just summarize what we had, the ideal op-amp assumption we just used here is IN was 0 and V positive is equal to V negative. And by the way, this condition is only for op-amps with feedback, or more precisely, negative feedback. And if we now focus on this amplitude gain is negative Rf divided by Rs. So only depends on the ratio to resistors, in other words, can easily change, right? The major problem I told you guys is if we use an open loop, that gain value is fixed and it's a huge value, it's an infinite value. So, well, everything is getting amplified to infinite, right? When we use as an open loop. However, in this case, you can change that gain, RF, RS, it's of your choice, right? If you just pick up like 10K and 1K, divide it, then it's going to be just 10, right? So you are boosting up by 10 times. You can pick like 5 and 2, then it's going to be 2.5 times boosting up. You see what I'm saying? You can easily change that gain value. So it's more like a real amplifier. And also, here is a negative sign. So it's the out is flipped or inverted. So that's the reason why we are calling this as an inverting amplifier. Any questions?
Yeah, if you choose your RS value to be larger, then also
yes.
increase.
Yeah, very good point. So the question is, what if we have this guy large value, say this is 10K and this is 2K? Then we have 1/5, right? So your input is getting smaller in your output, right? You shrink down your signal. That's possible too. Okay, good. Very good point. So let's try a very simple example. Say we had RS was 1K, or like 1K was connected here, and 10K was connected there, okay? And this VS, your input signal was 0.15 volt with 50 hertz sine wave. What's going to be your Vout? Your Vout is negative RF over RS times VN, right? I have to confess that I very oftentimes use VS or VN simultaneously. So hopefully you understand by the context, okay? So VS is almost the same as VN in general, right? And this is going to be what? This is 10K and this is 1K. So it's nothing but negative 10, right? Times VN is 0.15 sine 2 pi ft. F is 50 and T is time. So it's going to be negative 1.5 sine 100 pi T. So say you had an input that goes in like this. It's a sine wave with 0.15 amplitude. Then your output should look like this. See? Your amplitude is what? It's 1.5. Here is negative 1.5 and this is positive 1.5. And it's flipped over. You have a sine going in, you have it just flipped over because we have a negative sign there. Okay? So that's the reason why we call it as an inverting amplifier, because our signal was just inverted, flipped over. Got that?